Thank you for the introduction. Thank you all for being here. I know you are all hungry, so I will try to make it nice and with cool illustrations. So my name is Tom Zvagier. I'm a first-year PhD student at INRIA, supervised by Xavier Pennec. And today I will present you our accepted work entitled Rethinking the Riemannian Logarithm on Flag Manifolds as an Orthogonal Alignment Problem. So first of all, in order to motivate the use for flag manifolds in statistics, let me talk about subspaces. Subspaces are really important tools to have in your data analysis toolbox, and their importance is notably justified by the well-known manifold assumption, which roughly states that when you look at high-dimensional data, it actually lies close to a lower-dimensional subspace. And this has plenty of applications in dimension reduction, compression, domain adaptation, etc., etc. And here, we will only focus on simple linear subspaces. So in the sense that we will represent a dataset, a point cloud, as a linear subspace, and there is a canonical way of doing that is through a principal component analysis. You do a representation at a given lower dimension of your data by taking the principal subspace at a given dimension. And the right space for working with such subspace representations of data is what is called the Grassmann manifold or Grassmannians. It is the space of all linear subspaces of a given dimension k embedded in a larger Euclidean space of dimension n. This is a smooth Riemannian manifold, so we have a lot of nice properties, and it has also a quotient space structure as a quotient of the orthogonal group, and I may detail that later when talking about flags. And what is nice is that we know a lot of interesting properties for geometric statistics on those spaces, notably the geodesic. We have a closed form for the geodesics, for the Riemannian logarithm. We also know how to express the geodesic distance between two subspaces, and many of you may have already heard about subspace angle distances that have tons of applications in engineering and vision. And so with that, Grassmann manifolds are really ubiquitous spaces for applications in computer vision, subspace tracking, domain adaptation, affine invariant shape analysis, and so on and so forth. But sometimes modeling a dataset with one single subspace may not be enough. Actually, when you model a dataset with one given subspace, you erase the information on the hierarchy of the modes of variability of your dataset. Indeed, if we have, for instance, two distributions, two populations that live kind of on the same space, but which we want to discriminate, then sometimes we might be interested in the main modes of variation in this data, and they might be able to discriminate those two distributions. And here we can see that with a subspace representation, those two distributions are encoded the same way. And so an idea to take into account the hierarchy of the modes of variability is instead to represent datasets as a flag of linear subspaces, which is a sequence of nested subspaces of increasing dimensions. So you have also a canonical way of doing that, which is by doing principal component analysis at different scales, and then the sequence of principal subspaces will be naturally nested. Okay, so that was for the motivations, and now let me define a bit more in details what are flag manifolds. So a flag is a sequence of nested linear subspaces of increasing dimensions, and the sequence of dimensions, d1, etc., until dr, is what we call the signature of the flag. So here we have a flag of signature 1, 2, 3. You have an equivalent way of representing flags as a sequence of mutually orthogonal subspaces. So indeed, you just need to take the orthogonal complement of one nested subspace into the next one, and this is such a sequence. So here we have represented exactly the same flag as before, but as a sequence of mutually orthogonal subspaces. And actually, you might not know it, but be working with flags every day, since a natural example of a flag as a sequence of mutually orthogonal subspaces is the sequence of eigenspaces of a symmetric matrix. And so the type of such a flag is a sequence of eigenvalue multiplicities of your symmetric matrix. Now, what is nice is that you can represent a flag as an orthogonal matrix. Indeed, you can concatenate some rectangular matrices, Qi, which are themselves orthonormal bases for each subspace in the flag. And since all the subspaces are mutually orthogonal, now we are working in the mutually orthogonal representation, this yields, when you concatenate all, an orthogonal matrix. So you represent a flag as an orthogonal matrix, but the choice for such an orthogonal matrix is not unique, since you can take many different orthonormal bases for one given subspace. So actually, flags are more equivalence classes of orthogonal matrices. And if you go into the theory, you can show that the set of flags of a given type is a smooth Riemannian manifold with a quotient space structure being a quotient of the orthogonal group by some orthogonal subgroups relating to the rotations within the subspace of the orthogonal bases. So with that, flags are actually generalization of Grassmannians and kind of generalization of Stifel manifolds, even if it's not exactly the same. Okay. And before going directly to the problem in question, just I will give a short overview of flags in research. So flags have been long studied in pure mathematics. They have also some applications dating from maybe 50 or the past century, let's say, in multi-scale analysis, for instance, with wavelets, for multigrid analysis, if you want to do a mesh refinement in numerical analysis. Also for matrix decomposition through isospectral flow, which diagonalize some symmetric matrices. And so in statistics, the works are more scarce. Actually, you have first contribution from 2006, trying to tackle a generalization of independent component analysis, but where you don't assume independence within subspaces. So it's kind of a generalization of ICA. And as far as I know, the next important contribution was from Xavier Pennec in 2018, reformulating principal component analysis as the optimization of a global criterion on flag manifolds. And so this brings interesting perspectives in terms of multi-scale modeling of a dataset in terms of best and best approximating subspaces and also more robust variants. I won't detail the rest of the literature, but just 10 seconds for self-promotion. We did a recent paper that is now on arXiv, which is called Stratified PCA. And it's it's studying general generative models like probabilistic PCA from Tipping and Bishop, and gathering them all into a family of generative models, which is parametrized with flag manifolds. And so we have nice geometric properties and also a characterization of the space of models as a stratified set, which realizes a stratification of SPD matrices. So this is interesting in the context of model selection. Okay, so now let's go into really the heart of the contribution, the geodesic distance and the Riemannian logarithm on flag manifolds. So in case, if you don't know them, you have to know that there are two really important quantities to have to perform geometric statistics on manifolds, and they are related to trying to find an interpolating curve of shortest length between 2 points. Usually, this is a really hard problem to solve. You formulate it as what is called the geodesic endpoint problem. So you want to find a tangent vector of minimal length that allows to link one flag to the other. And so as far as we know, and to the best of our attempts, there is no closed form for such a logarithm. In the literature, there are 3 or 4 papers tackling it. One where if you read too fast a result, you think that they found a closed form solution for the logarithm, no, for the geodesic distance, but actually it's not the case. And then you have two other contributions relying on optimization, trying to solve relaxations of the geodesic endpoint problem with Newton-like methods or more with an alternating tangent space projection scheme. And the nice article, what is nice with it is that they give a practical application of representing datasets as flags. And it shows that computing geodesic distances between flags is more informative and allows to discriminate hyperspectral images compared to the more classical Grassmannian modeling. So now our contribution is to propose an algorithm for approximating the logarithm and the geodesic distance on flag manifolds. So we rethink it as an alignment. So what is an alignment? You have to know that when you want to look for a geodesic distance on quotient spaces and you know the geodesic distance on the top space, then you can find, under some particular conditions, the geodesic distance on the quotient space by minimizing the pairwise distances between the equivalence classes, each equivalence class representing one point in the quotient space. So it's as if you want to measure the distance between two walls in your house, you will put your laser on one wall and you will try to find the opposite point, which is the shortest from the one you shoot it from. Okay, and it will yield a horizontal beam light, and this will be the horizontal distance between your two walls. And solving this problem yields, in the case of flag manifolds, the log and the distance. So now our problem is a bit more complicated. The walls are curved, and the light beam is not a straight line, so it's more complicated. But still, we can kind of formulate this problem as an optimization problem and try to look for a solution. So if you want maybe an illustration of what we are doing, less conceptually, so imagine you have two orthogonal matrices represented by a triplet of points. One is full row and we'll call it P, and the second one Q, which is the one we want to shoot to. Then we have a closed form geodesic from one matrix to the other. It's given by the matrix exponential and matrix logarithm. And so the alignment step consists in moving the second matrix into its equivalence class, so such that the span, the subspace, is not changed, but in order to make it closer from the original matrix. And once the alignment is done, then the geodesic distance compared to the orthogonal distance between the aligned points. The issue is that even with this reformulation, we do not have a closed form for the alignment process. So the hopes are a bit small for finding a closed form for the logarithm. But a good news is that we relaxed this alignment problem using a Frobenius distance instead of the top space distance. Happily, fortunately, we found a closed form for this relaxed problem, and actually it is linked to orthogonal Procrustes analysis. And so what is nice is that as a first approximation, we can perform a first step of alignment to make the two matrices closer, and then we can incorporate this step into an iterative algorithm that will build a sequence of points Qt in the second equivalence class that are closer and closer in terms of orthogonal geodesic distance from the starting point. And so this yields actually, I will not detail, but it yields really interesting and quite surprisingly impressive results in terms of numerical accuracy, radius, and speed of convergence compared to previous algorithms that was proposed, the one with the example I showed you on hyperspectral imaging. Also, it solves some issues about connectedness of the non-connectedness of the equivalence classes. So it's quite interesting. And so to conclude, we propose an algorithm for approximating the log and the distance on flag manifolds, and it shows great results. To follow, we could better deal with high dimension by applying some linear algebra tricks that are quite common in flags or on matrix manifolds. And then the big open question is about convergence analysis of the proposed algorithm. So yeah, it was a short time contribution, so we didn't have time before GSI to analyze an answer to such a question, but if there are some optimization experts in the room, we would be glad to discuss about this algorithm. And then, also, so the work stratified PCA that I presented before, it also opens some new perspective regarding to this problem in terms of modeling data sets using flags of sparse signatures. So that's all for me, and thank you very much.
Thank you very much for this very interesting talk. So, questions? Directly.
So I think I should know by now, but I still don't know. What is, again, the distance d that is not the Frobenius distance?
Okay, so this is the orthogonal distance. This one on the left, you mean?
All right, this is your distance between your two walls, right? No?
Exactly, yes. So it's a quotient space of the orthogonal group by some orthogonal subgroups. And so you take the top space distance, which is the orthogonal distance, and the alignment consists in minimizing the top space distance, and we relax it with a Frobenius distance.
Orthogonal distance. All right.
It's like that. I love this GIF. It's the exponential of a skew-symmetric matrix, basically.
All right. Okay. Thanks.
Hi, so thank you for your very nice talk. It was very interesting for me because I'm interested in the same problem but on the Stiefel manifold. Mm-hmm. And I wanted to know if you had tried to use your algorithm with the fibers but on the Stiefel manifold, because we have the same problem with Stiefel manifold, which is the basic flag, and then you have these fibers that are made of the special orthogonal group.
Yes. No, I've not tried, but so let me think if it could apply, because we need this projection step on the fibers. So I guess we can. We can project an orthogonal group, an orthogonal matrix on the fibers. No, maybe. Yeah, I guess it could probably work, but I don't know if it's the most interesting. I don't know if it would compare well to the already well-developed literature of distances on Stiefel manifolds. But there is a paper recent from Nguyen. It was. I don't think I have the. Yes, I have it. This one, closed form geodesics for the Riemannian logarithm on Stiefel and flag manifolds. And so in this work, he kind of used the same algorithm on flags and on Stiefel manifold, but it's more of a shooting problem, trying to minimize the endpoint error based on the initial tangent vector. But so I will be happy to discuss with you if you have some ideas. Thanks.
Hi, thank you for the presentation. I'm really new in that topic. Can you please tell me some example where this can be used for? So I have really problems to imagine what you want to do with the logarithm and exponential on the manifold.
Yeah. Okay. So there is one example that I gave here. So I'm mostly familiar with the interest of the geodesic distance. So having a distance in general between points on a set is really useful. So it was told in the presentation of this morning. It's a way to compare some objects, and you can design a lot of learning algorithms with that. And in that case, it was used in the task of hyperspectral image classification. So you represent each kind of hyperspectral image as a flag, and so you compute pairwise distances between flags, and this allows to kind of locate and to embed in lower dimensional subspaces your hyperspectral images. So a lot of manifold learning and multidimensional scaling, etc. methods are relying on knowing distances between points. And for the logarithm, so Xavier knows better, but I guess for interpolation, interpolating between, I was talking about subspace tracking, domain adaptation. So I don't know if you really are familiar with this domain. Like it's when the domain of definition of your data changes with time. Sometimes it might be nice to interpolate between the subspaces. And so with flags, we could kind of do that in a multi-scale way. And the logarithm provides such a curve between 2 points.
Why don't you use that it locally looks Euclidean? What are the advantages you are doing that way? So it's manifolds or locally it's locally.
Okay, question is, why don't you use that it is locally Euclidean?
What's the advantages from the GUI?
Yeah, maybe in the interest of time, I'll give a brief comment on that, because for statistical issues, as you said at the very beginning of your talk, it's interesting to look at, if you do PCA, for example, it's good to look at several PCs. And actually, you talked about convergence, so you might not be aware, Benjamin Elston and I have a paper on statistical convergence, on a central limit theorem on flag manifolds. And this is very interesting if you want to analyze data on several scales. So this is it's very interesting to develop also the numerics that things work. So maybe that helps. And under certain circumstances, you can actually have a central limit theorem on flag manifolds.
Okay, I was not aware. I'm sorry.
That's okay.
I should. Okay, thank you.
Yeah, I think at this point, probably in the interest of time, we'll thank you once again. Thank all speakers here at this session. This was a great session. Thank you very much.